so far we've defined that an exponential function is going to have as its equation y equals b to the x, where b has to be positive and b isn't 1. What I want to do now is point out that the two patterns that we've seen, the one shape where it was always increasing and the one shape where it was always decreasing, are the two types of patterns that we can get. So that if you have an exponential function, you know the graph looks like one of those. So I want to first of all summarize that and then talk about these restrictions on the base and why we exclude those other values. So first of all, if I have y equals b to the x and b is bigger than 1, I'm going to have the sort of graph that I saw when my base was 2 or 3. We're going to have a horizontal asymptote on the left side, and the graph is always increasing. We call this exponential growth. The y-intercept is 0, 1. And I'll always have a point on it when my x value is 1, the y value will just be b. That point's going to be very helpful in determining how quickly it grows and how quickly it gets steep. And then, of course, over on this left-hand side, if my x value is negative 1, the y value will be the reciprocal of the base. So that's going to help me see the pattern on the left of, if we're reading it backwards, how quickly we decrease, getting closer and closer to 0. Okay? So those 3 points are going to be very helpful. I won't need a table of values anymore because I'll basically know the shape of things. If I have something like this, the domain, and this is going to be true for all exponential functions, is everything from negative infinity to infinity, and the range is the set of all positive numbers, so everything from 0 to infinity. I can describe my end behavior. I can say, as x goes off to infinity, b to the x goes off to infinity in this case. As we go far to the right, we just keep going up and up and up. But as x goes to negative infinity, b to the x goes to 0. So that would be the end behavior if I've got exponential growth. Exponential growth is really important in a couple of applications, which we'll see in a bit. Want to just point out that over here, where my y values are big, are also where the slope, or where the steepness is big, where the rate at which it's changing is big. Over here, where my y values are small, the rate at which it's growing is also small. So an exponential growth function is going to capture something that's increasing at a rate proportional to its size. Now that's incredibly important in the sciences and in economics. In the sciences, if I have a petri dish and I put some bacteria in that petri dish and I sprinkle it with bacteria food and I turn my back and then I look back again, oh my goodness, there are lots more bacteria in my petri dish. Assuming that there was enough space for them to grow, they were going to grow, and they were going to grow at an exponential rate. Because once the population is bigger, that's more bacteria to be reproducing, so they're going to be reproducing at a faster rate. When there's a small population, there are very few bacteria to be reproducing, so they're reproducing at a slower rate. Okay. In the financial world, interest, if it's compound interest, where you're either earning interest on the interest or paying interest on the interest, things grow at an exponential rate as well for that. Okay. All right. Now, if I have y equals b to the x, but the base is between 0 and 1, so we looked at 1/2 to the x as an example there. Then we saw that we had something that looked more like so. It was always decreasing, and we would call that exponential decay. Now, we do still have that this function represents something that's changing proportional to its size. It's just decreasing. when the y values are big, the rate at which it's decreasing, which is represented by the steepness of the graph, is also big. When the y values are small, the graph is not very steep, so the rate at which it's decreasing is rather small. Okay. This is important as well in the sciences. Radiation decays at an exponential rate. Okay. So for a lot of medical tests, okay, you go to the doctor. This is the person who's supposed to keep you healthy or make you healthy, and the doctor injects you with radioactive stuff. That doesn't seem like a good thing. Okay. But they do that if they need to do certain scans, because that radioactive stuff, I guess, somehow shows up on the scans, and then they're able to see what's wrong with you so that then they can fix it and all of that fun stuff. Okay, but the basic idea is this. Generally bad idea to have radioactive stuff inside of your body, right? So they inject you with as little as possible, but then the amount of radioactive stuff that's in you is going to be decreasing, and it's decreasing at an exponential rate, so that it's going to be in your body forever because you've got a horizontal asymptote. It's never going to actually hit zero here, okay? But at the moment when there's enough there for the doctors to see stuff, that only lasts for a short period of time, and the amount is decreasing fairly quickly, and then it gets down to such a small amount that it's really negligible and you're okay. All right. Okay, so we call that exponential decay. If you have a graph like that, the y-intercept is still going to be 0, 1, because 0 to anything to the 0 power is going to give me 1. It will still be the case that if I plug in 1, I will simply get whatever number is my base. And that number is going to help me see how quickly we're decreasing towards this horizontal asymptote. If my x value is -1, we'll have the reciprocal of b still. But now notice if b is a fraction, like when b was 1/2, the reciprocal of b was 2. So that the reciprocal of b is much bigger than b is. And so that's going to help me get about the right steepness over here on the left side of the graph. So again, those 3 points are going to be very, very important. Again, we have a horizontal asymptote on the left. Let's see, I can say that my domain, as with any exponential function, is everything from -infinity to infinity. I can say that my range is everything from 0 to infinity. Again, it's the positive numbers. This one's just always decreasing. And so the end behavior looks different. As x goes to infinity, b to the x goes to 0 if the base is between 0 and 1. And as x goes to -infinity, b to the x goes off to infinity. As we go to the left, we go up. So these are the 2 types of shapes that we get. Okay. So one situation, exponential growth, if the base is bigger than 1. Exponential decay if the base is between 0 and 1. Now, I want to talk about the bases that we don't allow. Okay. So in saying that the base has to be bigger than 0, but not equal to 1, we're basically saying 3 things. The base can't be 1, the base can't be 0, and the base isn't negative. So I'm going to look at 2 very specific numbers, 1 and 0, that we don't allow the base to be. And then just lump all negative ones together. Okay. Now, if b was 1, certainly 1 to the x is perfectly well defined. Y equals 1 to the x is just 1. It's a perfectly good function, but it's a constant function. We already have a name for it. We don't count that as an exponential function. The pattern that we see in exponential functions is that they're changing, either increasing or decreasing, at a rate proportional to their size. This isn't changing at all. Okay. So it's not that the function isn't defined, it just doesn't earn the designation of being an exponential function. It's a constant function. Now, we don't allow the base to be 0 either. I could define a function y equals 0 to the x, and it would have kind of a strange looking graph. At 0, it would be up here at 1. To the right of 0, it would be at 0. and it wouldn't be defined to the left of 0. Okay, so if I've got a positive exponent, 0 to any positive power is just 0. Okay, 0 to the 0 is defined to be 1. Okay, some people say, oh, that's undefined. It actually is defined. It is 1. Anything to the 0 power, including 0, is going to be 1. Okay, seems like perhaps a strange rule, but that's the definition. But I can't have a negative exponent because negative exponents put things in the denominator. I can't have a power of 0 in the denominator because that would put 0 in the denominator, and we can't divide by 0. So we get something with a different domain, some sort of weird behavior at 0, and then it's constant to the right of 0. Okay, I can define that function, but it doesn't earn the designation of an exponential function. Okay. Now, why don't we allow the base to be negative? In this case, that's just because the domain would be a nightmare. Okay, if I had a negative number as the base, let's just say we had -2. Well, then I can't take that to the 1/2 power because that would be the square root of -2. Now, in the complex numbers, I can do that, but we are working now in the real numbers. The only time we were really working in the complex numbers was with polynomials because that allowed us to find n zeros for a polynomial of degree n. We're very concerned with graphing these things, and anytime we're graphing, we're working in the real numbers. So I can't take a negative base to the 1/2 power, but I also can't take it to the 1/4 power, or the 3/2 power, or the 1/8 power, or the 3/8, or the 5/8, or any fraction with an even denominator. So if you imagine taking your number line and removing every fraction with an even denominator from it, you've got infinitely many gaps, you've got infinitely many points left, but as I mentioned, the domain would simply be a nightmare. So we simply don't work with negative bases. So, different reasons for restricting things. This is just a different sort of function. This is kind of boring, doesn't earn the name of an exponential function. This is kind of weird, doesn't earn the name of an exponential function. This is kind of nightmarish, doesn't earn the name of an exponential function. So an exponential function is a positive number to the x where that positive number isn't 1, and that means that we've got two types of exponential functions. If the base is bigger than 1, we will have exponential growth. If the base is smaller, between 0 and 1, it will be exponential decay.